Okay. So the goal is to somehow create a central simple algebras package in Julia, which will eventually integrate or be incorporated into the Oscar open source computer algebra package. The problem is that I'm not a programmer, so a lot of this is just me learning, and we're going to see how it goes. The first thing that I pretty much have to come to grips with, or like figure out, is essentially how to construct a non-commutative ring from kind of a centrally defined class of central simple algebras. So this is kind of the first main goal for me. All right. Probably the best thing that I could find is, I mean, if they still have, like, vile algebras, I think that is part of the Oscar package. So if I could find Oscar source code that makes a vile algebra, it's probably, like, the best thing that I could find. But okay, PBW algebra, I think that's probably about as effective. So we've got PBW algebra ring. It's got two types for parameters T and S. It's going to be a non-commutative ring. It's going to take in a string, singular.plural ring. That's going to have relations, singular.S matrix of type singular.S poly. There's going to be a coefficient ring, there's going to be a poly ring, and there's going to be an opposite. So the string is the thing that kind of confuses me at the moment. Is that just going to be a set of generators? Also, the type plural ring, I don't know. We could probably find that though. Singular plural ring. What should I add here? Computer algebra. Plural is a kernel extension of singular, providing many algorithms for computations within certain non-commutative algebras. It uses the same data structures, sometimes interpreting them in a different way and or modifying them for its own purpose. In spite of such a difference, one can always transfer objects between commutative rings or singular and non-commutative rings. With plural, one can set up a non-commutative G algebra, say A, with a Poincare-Birkhoff-Witt basis. Functionalities of plural are accessible as soon as the base ring becomes non-commutative. One can perform various computations with polynomials and ideals in A and with vectors and submodules of a free module. What is a G algebra? In mathematics, a G algebra can mean either an algebra over a field, with an algebraic representation of G, or a G ring that is also an associative algebra. G ring is a Grothendieck ring, Noetherian ring, such that the map of any of its local rings to the completion is regular. It's hard to believe that that is the thing that they want to use. And I don't know why that would be some kind of type. That's possible to set up. I don't know why that would be a type that you can set up in a computer system, but maybe that is what they want. So, definition of a G algebra: let K be a field, and let a K algebra A be given in terms of generator subject to the following relations. So this one just says A is kind of non-commutative polynomial ring of variables x1, xn. And there's product rules where xj, xi is some coefficient times xi, xj plus some other coefficient. And then A is a G algebra if there's some following conditions that hold. So there's a monomial well ordering on the polynomial ring, such that for every I less than j, the leading monomial of one of the coefficients in the defining relations is less than xi, xj. So I think LM is leading monomial degree. And there's some non-degeneracy conditions. Okay, so some polynomial in terms of the relations is assuming not zero. I mean, oh, it is zero. Yeah, and then the non-degeneracy just says that it's associative. Okay. All right. So we can mimic, I think, most of this still. So we're going to do why do we have two types, for example? I guess it's because string and relations are going to be different. But I want singular plural ring type S, singular S matrix of type, singular S polynomial of type S. Alright, I don't know why everyone uses mutable struct also, but we're going to try it. So what do I want for types? Parameterizing this guy. What do I want? this data type to contain. So it should contain a list of generators. Oh, this is S ring, not string. S ring. So it's going to be a singular plural ring relations. It's also going to contain coefficient ring and poly ring. That's weird for the PVW algebra. What we want, right, is just a maybe an NC ring. So let's do NC poly ring. Which is going to be exactly what it is. So it's going to be NC. I hate that there's an NC poly ring element, but not an NC poly ring. There is a type though, NC poly ring. Okay, so we're just going to leave that there. There's going to be some relations. I'm going to call this just ideal. And it should be of type, well, ideal inside an NC poly ring. So I feel like there should be an NC ideal type. Could store it as just a list or a vector of elements from the NC poly ring. So the one thing that I don't know about is that, first of all, we got to look up the abstract algebra type system. And NC ring is of type ring. NC polynomial ring is of type NC ring. No, ring is of type NC ring. Oh, okay. So ring means commutative specifically. So we can't do ideal there. So let's look up ideals. And NC ring, abstract algebra. .jl, which is constructed in the generic ideal. But this is of type ring. So it lied to me. So we could do free algebra constructors. If this is more likely to contain ideals. The following helper enables things like ideal R bracket or ideal R bracket 1. Type check ensures we don't run into an infinite recursion. I think that ideals might just work for so I think I can just say that this is a ideal, or is it going to be an ideal type? Never have any idea. Okay, so these are all inside genuine rings. And this one is also, okay, so I think ideal type is inside of ring. What is inside of non-commutative ring? Actually, it's not clear. It's not clear because ring is inside non-commutative ring. But why would you have anything other than commutative rings listed as rings? All right, we're asking Gemini. Where is the functionality for non-commutative ideals? What should I actually ask? What is the type? Is there a type for non-commutative, for ideals and non-commutative polynomials in abstract algebra .jl? Yes, it provides a type for ideals. While abstract algebra supports NC polyring for non-commutative polynomial rings, documentation indicates that a more complete implementation for ideals over rings other than Euclidean domains or is provided by other packages like Hecker or Oscar. However, you could still construct ideals using the generic ideal ring vector constructor where R is the ring, which could be an NC poly ring. Kind of not convinced that it could. So we can do this, right? Just let's start up a Julia interface and try copying the code. Right, so I didn't include using Oscar. Awesome. Non-commutative. I spelt everything right. So we have to assume that. Let's try using abstract algebra. Let's try non-commutative polynomial ring QQ X Y. Let's just try it again. Okay, still didn't work. So now I just gotta assume that Gemini's lying. Sometimes I think that, right, so it's deprecated, probably, or it just doesn't exist. Yeah, I think that there still is a constructor function for non-commutative polynomial rings. So we're going to just check and see. This is specifically NC Poly. What I want to know is if there's an NC Poly ring or some kind of there's free associative algebra, which effectively is, right, an NC polynomial ring. But the base ring is different. So let's see. What is the constructor function for these things? There it is. Okay. So we can try. We're going to try doing effectively the same thing, but instead of non-commutative polynomial ring, we just do free associative algebra. Hint: a global variable of this name also exists in abstract algebra, also exists in Nemo. QQ was not defined in main. Sick. Looks like 2 or more modules export different bindings with this name, resulting in ambiguity. So if I run QQ, that's just it. So I have to write something crazy like nemo.qq. Okay. QQ equals nemo.qq. Can I do that? Alrighty. Now we run it again. And great, we got free associative algebra on 2 indeterminates over QQ. And if I call, so now how do I set up an ideal? Gemini's suggestion for an ideal might not have been bad. So if I would say something like G is x times y minus y times x. Can I make commutative algebra? So we'll say I is generic ideal. There's no way that this is the actual interface for generic ideals, right? So it says that there's no method for this function call. Okay, so this function call doesn't make sense on these types. Which could be 2 things. So it could mean that it doesn't... I think this is the most direct problem, right? Is that we need a ring and a vector of ring elements. And what I produced was a ring, but a non-commutative ring. And specifically a free associative algebra. And so I think it's just not going to like that. So what about free associative algebras? Is there an ideal constructor in this setting? I think it's lying to me. So it just says call the same shit that I just called. Oh, but right, maybe that's it. So there is some computation, I think, in singular where you can construct ideals. So I think maybe in singular you can construct ideals using non-commutative. So I think in singular you can construct non-commutative rings and ideals. Fuck. I know that there's an interface for singular in the Oscar Julia package. But it just seems so difficult. So here's the question. Right, I think abstract algebra has no functionality for ideals in free associative algebras. I want to know if you can construct quotients by ideals, mostly. That seems like something that, you know, you'd fucking hope that this could answer. So, you construct quotients of non-commutative rings in abstract algebra. .jl. Yeah, I think that you have to use singular somehow. Stack Overflow answer from a maintainer suggests that while general quotient rings weren't fully available directly in abstract algebra in 2021, they are available through Oscar. Right, probably using singular. So, how do we construct a singular non-commutative polynomial ring and ideal? Right, so we're going to call singular. I don't want to construct specific ones like this, so let's do free algebra. I wonder if this call from before different variable call. So the function free algebra exists, but no method is defined for this combination of crap. And the problem was the singular field. Okay, so QQ equals singular dot QQ. Does that work? Can we call it now? Int 64 is another thing that we need. Abstract vector and then comma int 64. Oh, because I have to tell it like a bound when it terminates, right? So 10. That might not be that problematic. Since we're going to do finite dimensional algebra at the end of the day. In this setting, if I want to do something like g is x times y, and then I want to construct this ideal, okay, it seems legit. Also, why are the lists of variables xy, 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 xy with 10 of these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it just repeated. It just made 10. It made 20 variables. Is that it? I hate this. The free algebra procedure creates a free algebra respectively the free bimodule of rank k, subject to a monomial ordering corresponding to the one of the original commutative ring, polynomial vector arithmetics in this k algebra, usual one. Let's define an ideal I as a list of polynomials in the free algebra and run, for example, 2 std. We get a two-sided Grobner basis for the ideal. Okay, so I have to look up singular free algebra. See what the documentation says. I don't like interacting. I'm not gonna lie. I don't like interacting in the singular database just because shit is not as well spelt out. Syntax, free algebra, ring expression R, int expression D, creates a free letter place ring with variables of the ring R up to degree D, the length of the bound, with monomial ordering determined by those on the ring R. So what does this mean? So we call R ring. No, what the fuck is this? Let's go to Oscar's. Fuck.
Should we just try Macaulay too? The problem is that part of the reason why we were looking at
Julia's environment is just because Macaulay 2 is also somewhat not fun to play around with. So the package NC Algebra uses curly braces to find non-commutative rings, whereas this package uses angle bar lists. So there's a non-commutative algebra and there's a socioalgebras. And they're separate. I think the NC algebra is the one that's more documented. So in this one, we can just define an ideal. I don't want to write Macaulay 2. Holy shit. Okay, so let's just try to see if we can find some documentation in here for arithmetic is delegated to the singular implementation of exterior algebra, which does automatically reduce after multiplication. To achieve this, a new pointer to the singular ring is needed. This pointer is new data field, S ring, in PBQ algebra. All right, maybe we look at the documentation. Maybe a non-commutative, maybe a non-commutative polynomial ring is a PW algebra or G algebra. So right, the nth file algebra over a field is the PBW algebra. But given a multivariate polynomial ring R over a field, given a strictly upper triangular matrix with relations, We have to have non-zero scalars there, though.
This shit, though, makes me think that this kind of makes me think that you can construct okay, so can you construct quotient, non-commutative quotients in singular? Oscar, Julia. Okay, so what we're looking for are quotients. Constructive GR algebra proceeds by taking the quotient of the G algebra by a two-sided ideal. Continuing with some examples from above. Okay, but this is in a commutative polynomial ring. We could look up Hecka. That's true. Okay, see if there is some sort of non-commutative algebra that we can do in here. I mean, okay, what's the problem? The main problem is that there's no explicit Grobner basis for a non-commutative polynomial ring that's implemented in the fucking Julia world right now. And in order to construct a non-commutative quotient, define non-commutative arithmetic, we'd have to implement this non-commutative Grobner basis. That's something that we could do. It's not like impossible. It is not something that I was planning on doing. Ugh.
All right. How do we figure this out? Generic algorithms for dense univariate arithmetic. Currently, only Karatsuba multiplication is implemented. Okay. Karatsuba multiplication is not bad. Finite field generic functions. Okay, so the real thing that I'm wondering is how do we see what's implemented in Oscar? Is like the thing that I actually, Oscar's kind of a big mess, right? Like, it just has a bunch of crap in it. Okay, so this is kind of what I was looking for, actually. Just to see if there was some documentation on how the Grosvenor basis was implemented. To see if it's all commutative. Okay. Let's ask Gemini how singular is implemented in Julia or in Oscar. How is singular interfaced in Oscar.jl? Our calls somehow. I mean, like, if I call like a singular function, is it somehow parsed into like a language that is not Julia and then interpreted in that language in some way? Is a singular ring, for example, a type in another language, not Julia? You've hit upon a fundamental aspect of how Oscar and its underlying components like singular work. It's a prime example of Julia's excellent interoperability with C and C++ libraries. Here's a breakdown of how singular is interfaced in Oscar and the nature of the types that you encounter. Singular is a C++ library. Singular itself is a powerful computer for algebra. I hate how often AI says powerful, but this is itself a computer algebra system implemented primarily in C++. It specializes in polynomial computations, Grosvenor basis, singularity theory, and related areas. The core algorithms and data structures of Singular are written in C++. Singular.jl is a Julia package that provides an interface to the C++ Singular library. It doesn't re-implement Singular in Julia. Instead, it acts as a wrapper that allows Julia code to call and interact with the underlying C++ functions and data structures of Singular. Does that mean that if you were going to write some
crap on top of the singular interface that it would have to be in C++. Instead, it acts as a wrap. Instead, it doesn't re-implement singular in Julia. Just acts as a wrapper. It avoids the need to port millions of lines of complex C++ code to Julia. How does it avoid that? A key component in this interfacing is the Julia package cxxwrap. It's designed specifically for wrapping C++ libraries in Julia. This allows developers to define how C++ classes and functions should appear in Julia. It handles the low-level details of memory management, type conversions between Julia and C++, and function call conventions. Essentially, you write C++ code that exposes certain singular types and functions. And cxxwrap.jl generates the necessary Julia bindings. When you call a function like singular.polynomialRing in Julia, it's actually calling into the C++ singular library through these generated bindings. Are singular rings, etc. Julia types? That's what I really want to know. When you create a singular ring in Julia, the object you get back in Julia is indeed a Julia type. For example, it might be something like singular.polyring singular.sPolyNQ. However, the contents or underlying data of that Julia object is typically a pointer to a C++ object managed by the singular library. Julia's garbage collector is often hooked up to ensure that when the Julia object is no longer referenced, the corresponding C++ memory is properly deallocated. This means that while you interact with it as a normal Julia object, its internal representation and the heavy lifting computations are happening in the compiled C++ singular library. Where can I find this? In the oscar.jl source code. So abstract types, this file often defines the Julia abstract types that represent singular concepts like abstract singular ring or abstract singular poly. Files related to specific singular modules functionality, you'll find things like rings.jl, like that defines polyring, free algebra, GA algebra types and their constructors. Polynomial.jl defines the S-poly type and methods for polynomial and arithmetic. Ideal.jl defines the ideal type and ideal related operations. libsingular.jl. So first of all, it says that in the why don't we just click this one? This is singular. This is just singular.jl. And then what's this? So it's just, is this what I'm supposed to use? S ideal? So I think there's some way to, oh, I have a singular ideal. So how do I construct a quotient? I just take a quotient at this point? Yeah, what the fuck am I doing? Q equals R mod I. Can I just do that? Should I call this singular dot quotient ring? So what was the issue that I was thinking about when I was thinking of this? Singular dot ideal is totally fine, but I was looking for how this is. Yeah, so I somehow I'm tired, I guess. So I can create a free algebra. I can create an ideal. I guess I want to know is I two-sided or not, but I took a quotient, so should be two-sided. And now let's see if I do. Can I count like? It's like, what are the fucking generators for this thing? For example. Okay, singular might be able to actually do this. So maybe these need to be singular rings and singular ideals. Singular.jl's Julia interface to the singular computer algebra system was written by Alexander Motsak, William Hart, and other contributors, and is maintained by Hans Schoenemann and Max Horn as part of the Oscar project, which is supported by the Dutch Forschungsgemeinschaft, DFG. Okay. Features of singular so far include singular integers, multivariate polynomials including several non-commutative variants, ideals over polynomial rings, free modules, Grosvenor basis over a field. Can I do two-sided std of I? Can I do singular dot two std of I? Can I do std of I? Can I do two std of I? Can I do singular dot two std? Okay, fuck it. Since this uses the letter place backend, I hate how much of this is like so just piecemeal, honestly. Used in the experimental letter place extension of singular. The crazy thing is, right, letter place is like, This shit is all fucked up in the sense that like it's what? Yeah, issued in October 2009. That's the weirdest statement I've seen in a while. That if you have polynomial ring, it's not Noetherian. I guess I believe that. But a two-sided Grosvenor base of a finally generated angle might be infinite. Or it probably usually is then, right? I mean, maybe it's not usually actually. So there is a Grosvenor basis for associative algebra somehow implemented in here. Oh, you can do gens. Let's clear all this shit. Let's just quit. Exit. My bad. Let's do Julia again. We're gonna do using singular. Now we're gonna do virtually the same shit, so wonder if there's any problems now just calling. I wonder if I'm gonna try this. I don't know if it'll work though. Okay. What? Oh, it just needs probably right. So why does it need a degree bound? We're gonna do 10 again. I got a bunch of... I got this vector which just doesn't make any fucking sense to me as a display. I've got some numbers. Virtually also don't make any sense to me. We're gonna try... why would they implement this degree bound shit? I don't get that at all. Is that somehow needed? Maybe because of this fact that you could just print some conceivably infinite list of generators because the ring is non-Noetherian. When you do some thing like this, I don't know. All right, so let's try it. So I is going to be ideal of R with some just anything really. So we'll do XY, YX. Okay. Now I want to do student of ideal of I. Okay, this was totally fine. Gens of student of I. Okay, So what if I do something else, like add 1 here, and then like subtract x here, and then I do std of I. Oh yeah, it kind of does fix that. Yeah, okay. And now let's do q as being r mod I. Let's do q as being quotient ring Ri. Deal must be a Grobner basis. Std of I. Let's do gens of q. Should be virtually nothing, right? I mean, I guess something that I don't know is like, what do they even mean when they do this Grobner basis thing? So x squared times y plus y squared. Type of this thing. ColorfulAlgebra. SLP alg NQ. For R, was it NR? No, right? It was also NQ, I thought. Yeah. Okay, so how do you do anything in the quotient? Okay, we got is quotient ring Q2. We could do a Q2 XY quotient ring Q1. It's std ideal. Is that what I'm missing? Okay. What the fuck is the point of the quotient ring in singular? What can you do with quotient rings other than compute? Probably some thing on I mean, you might be able to compute some algorithms. You might be able to compute like Hilbert polynomials just because you know the ring and the ideal. But then I don't understand why you'd list it as a quotient ring. So I feel like you should be able to take an element like x squared and then reduce it in the quotient ring. So how do I, okay. So let's start a new guy. So let's say R is a singular .jl ring and I is an ideal in that ring. How do we reduce elements in R mod I? So reduce x squared in I. Incompatible base rings. Sick. We need to clear all this shit. Alright. That didn't work. Let's start again with this. And then we do I. And then we do this. Does that make sense? It does. What if we do that? Okay, -1. Interesting. What is the point of the quotient ring? R mod I in this language. Is incredibly powerful. I don't know, man. Seems like some fucking bookkeeping. Oh, I guess maybe you could do, I mean, but then you could just do reducing an ideal J mod I or something like this, right? Like, how do I access generators in R mod I? When you construct a quotient ring, the generators are the images. Sure. Something that provides a convenient way to get these directly when you define the quotient ring. How is that? Oh, you just define a new set of variables, huh? So like Q, you do X prime, Y prime. It's probably not a good numbering system. I hate also that I can't scroll down further. So we'll do X sub 0, Y sub 0 is quotient ring Ri. I think you need Grosvenor basis, so we do std of I. Okay, now I can just do like what? X sub 0 squared. We're actually gonna do X sub 0 times Y sub 0. It's X times Y. But isn't the point that this was supposed to be -1, right? Yeah, so what the fuck is going on? You can now perform arithmetic with these elements in the quotient ring. Oh, I should have to type in the relation in Q or what? I don't think this is true to some extent. I mean, I guess it makes... Yeah, no sense. Oh wait, it was plus, right? It doesn't make any fucking sense. Maybe I just have to do it all over again. Maybe I fucked something up in the middle.
It just doesn't make any sense. So, the valuation x bar squared minus y bar outputs x squared minus y. You are absolutely correct to point that out. I think Gemini doesn't actually know this. My apologies, there's a slight misunderstanding of my previous explanation of the output. This evaluates the zero element in the quotient ring. Singular often displays the normal form of the element, which is the unique representative in R that corresponds to the element in R mod I. That doesn't make any sense. Does it not make any sense? When you see this as the output, it means the system is telling you that the representative element that in the original polynomial R is x squared minus y. Since x squared minus y is one of the generators of the I, its image in this is indeed the zero element. Sure, but how can I see that as an output? I mean, I can just say something like this, right? Like, I can just say equals 0. True. Okay, that's not a bad thing, actually. That is not bad. I wish it just fucking output it, though. I mean, like... I mean, I don't understand why why when you evaluate it, it doesn't automatically reduce it. Like, it's fucking stupid, I'm not gonna lie. To call, like, the images like this and just to get the original output back. To have to check that, like, that is 0 is just fucking insane. I think maybe to do something like, yeah, I mean, it doesn't make any sense to do this either. Like, so... Alright, I'm not gonna... beat around that too much. So how does singular do arithmetic in the quotient ring? Singular performs arithmetic in quotient rings by leveraging the power of Grobner basis and normal forms. When you construct this for Grobner basis of I, Grobner basis, elements in Q are represented by polynomial rings in R. An element is internally just a polynomial. An element like x bar in Q is internally just a polynomial x from R. When you create x bar squared, it first computes x squared. Arithmetic operations are performed in R first when you add subtract elements. The result is reduced using a Grobner basis. After any arithmetic, the resulting polynomial is immediately, or is needed, reduced modulo the Grobner basis. This reduction process finds the unique normal form of the polynomial with respect to g. This is where the reduce function comes into play. It effectively performs multivariate polynomial division by the elements of the Grobner basis on the more reductions possible. The property of a Grobner basis ensures that this normal form is unique. Blah, 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 blah. So it's claiming that if I did this example, Q join XYZ
I is x squared minus y squared minus z. It might be true in not non-commutative situations. It might be true in it might be true in so like if I did r x y is, I don't even know what the notation is in this one. Okay, so let's just try x y. Gosh, darn it. I don't know what the polynomial ring constructor is in this in singular. Sick. So if I do, it says x squared minus y squared minus, we're doing x. We're doing q x 0 y 0 is quotient ring of r with std of I. What was it, lowercase? Fuck. It was supposed to be capitalized. I wonder if I can just do r mod I. So apparently it doesn't want to do Grosvenor basis on I. Oh, I's a tuple. Fuck. 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 Bro. Oh, I'm not defining the fucking ring first. That shouldn't have been needed. I'ma say it. Maybe it wouldn't have if I had cleared the cache or something. Okay. So, now I should be able to do this. Okay, and now if I do x0 cubed or something, replies x cubed, x0 cubed minus... Oh, this is gonna piss me off. Oh, it's gonna piss me off. Alright, I think I'm checking out then. Fuck it. At least now I feel like I'm supposed to be doing this package construction in singular. It at least has functionality for doing non-commutative Grosvenor basis, which is needed just in order to count the dimension of a central simple algebra, for example. So I'll just make a note of that. Should use singular objects instead. All right. Was that productive? Kind of don't think so. But we'll try again next time. Night.